Hello, in this video I'm going to talk about a famous identity among vectors in 3 dimensions, which is called the BAC-CAB rule. So what is the BAC-CAB rule? If I have 3 vectors, say A, B and C, I can cross product B and C to get a vector, and then I can cross product A with the result. So the answer to this turns out to be B multiplied by A dot C minus C multiplied by A dot B. And the way you read it, it makes it easy for us to memorize. This is read BAC and this is read CAB, and then it turns out that this combination is equal to this cross product. Okay, so how should we prove that? Of course, one way to prove this, probably the easiest way or more straightforward way, is to write A in its components A1, A2 and A3, and do the same thing for B and do the same thing for C, and then using the analytic form of the cross product and doing a lot of algebra, very easy algebra, we can find the 3 components of this vector and then keep it aside and do the same thing for the right hand side, and then compare the results. You immediately realize that these two are exactly equal. But here in this video I want to approach the proof from a geometric point of view, and I don't want to use any algebra. And probably the most elegant proof for this, you can find it on in text on mathematical physics, that they use the tensor notation, and I will also present that at the end of this video for the students or for the people who are interested and familiar to those kinds of things. But before that, I want you to understand that the form on the right hand side is predictable for us even if we don't know the formula. Why is that? Because if I ask you what is A cross B cross C, you will definitely tell me this is a vector which is perpendicular to A, because that's the cross product of 2 vectors. One of them is A, so definitely it is perpendicular to A. And on the other hand, this vector is also perpendicular to B cross C itself. Yes? But we already know that B cross C is a vector that is perpendicular to B, and B cross C is perpendicular to C. Okay, now let us see what happens. This vector is perpendicular to B cross C. We need to imagine it. B cross C itself is perpendicular to both B and C. So this means that this vector will live on the plane of the vectors B and C. And in that case, this should be a linear combination of these 2 vectors. So this means that there exists x and y in the set of real numbers, so that A cross B cross C is equal to some number x multiplied by B plus another number y multiplied by a vector C. The whole point is that what is x and what is y? We want to find them. So I need 2 equations because I have 2 unknowns. And then we are going to show that this x is actually what is predicted in this formula, and that is A dot C. And we want to show that y is actually minus A dot B. It turns out that finding one equation between x and y is very easy, and the other equation will be a little bit problematic and tricky. Okay, so what we do, for example, you can take this equality and multiply A by dot product on both sides. Okay, and then this will immediately give you an equation. Why? Because if I do the same thing that I mentioned, then I will have this situation. Yes, and then A dot on the right hand side, I can distribute it. It becomes A dot B plus y A dot C. But on the left hand side, as you see here, this vector is orthogonal to A. So whatever it is perpendicular to A, and if I multiply by dot product a vector by a vector which is perpendicular to it, the answer becomes 0. So I immediately get an equation here. So I know that x A dot B plus y A dot C is equal to 0. So you see that one equation between x and y is very easy to find. Finding the other one needs a little bit of effort. Okay, my strategy to tackle this problem for finding another equation for x and y is completely different. I don't want to follow this exactly here right now. I want to prove actually this BAC-CAB rule for particular cases. The first particular case that I want to prove for you is that I want to consider this case that I have two unit vectors, vectors of unit length u and v. I want to prove that the BAC-CAB formula actually holds if I have this situation. I want to show that the same rule applies if I have this scenario. So you see I have more or less the same combination as the BAC-CAB rule. I have two cross products, but vectors are unit vectors, and the other point is that one vector is repeated. And I want to show that this is indeed equal and it follows the same BAC-CAB rule. So I want to show that this is indeed the case, that this becomes this minus v. The reason that this is just v, because in principle if the BAC-CAB rule is right, then I should write v times u dot u, but this becomes norm of u squared. U is a unit vector, so it becomes 1. So anyway, I want to have two vectors u and v, and I want to show that this is valid. Okay, I consider two scenarios. Yes, I would say that I would consider two cases. One case is that u is parallel to v, and I will show that in this case the left hand side is equal to the right hand side. Sorry, these are unit vectors. Okay, if u is parallel to v, and because u and v are considered to be unit vectors, then it means that I have two possibilities. Either vector u is exactly equal to vector v, or vector u is opposite to vector v. Yes? Okay, what happens if u is parallel to v? If u is parallel to v, we know that u cross v becomes the zero vector. And this means that the left-hand side of this equality that I am going to prove, the left-hand side, vanishes and it becomes the zero vector. But what happens for the right-hand side? For the right-hand side, I can consider two cases. Either u is equal to v or u is equal to minus v. Okay? So for the right-hand side, I can consider two cases. One, u is equal to v. Then what happens? The right-hand side, wherever I see v, I put u. On the right-hand side, I have u times u dot v, but instead of v, I put u, minus v, again I put u. But if I ask you what is u dot u, it is the norm of u squared, but u is a unit vector, it becomes 1. So then it becomes u minus u, and this is the zero vector. So the left-hand side 0, the right-hand side 0. But then it might happen that I have u equals to negative v. Then the right-hand side becomes what? Instead of u I put u, but instead of v I put minus u. So it becomes u dot minus u, and then minus minus u. So it becomes minus u plus u this time, and this becomes the zero vector. Again, they are equal. So it means that if u and v are parallel, then this rule applies. But what happens if u is not parallel to v? But before moving, let me write a remark here for you. Since u and v are unit vectors, we can write that u is parallel to v. Sorry, I have to write this. U is parallel to v if and only if u dot v squared is 1. Why is that? Because if u and v are parallel, it means that they are unit vectors, so it means that they can be like this, so the angle between them is 0, or they can be like this, the angle between them is pi. Okay? And then u dot v becomes the norm of u, which is 1, multiplied by norm of v, which is 1, multiplied by cosine of theta, which is cosine of 0 or pi. So cosine of 0 is 1, cosine of pi is minus 1, so it becomes plus or minus 1. So u dot v is plus or minus 1, so if I square it, it becomes 1. On the other hand, if this is the case, it means that u dot v is equal to plus or minus 1. So this means that the cosine theta is plus or minus 1, so it means that theta is 0, or pi. In any case, it means that they are parallel. Okay? Okay, and now we consider the case for which u is not parallel to v. In other words, u dot v squared is not equal to 1. Okay, so what happens in this case? U is not parallel to v. We want to see what happens. Of course, according to the remark, it can translate itself to this thing, that this 1 squared is not equal to 1. Yes? Okay, in that case, we have the same idea that I described. This vector, again, in this situation that they are not parallel, lives in the same plane as u and v. Yes? Have two numbers, so there exists real numbers m and n, so that this combination is equal to m times u plus n times v. Yes? Okay, now what can I do? Again, I can easily find an equation by dot producting both sides by u, so it becomes u dot u cross v. The right hand side becomes m u dot u, which is 1, plus n u dot v. But again, this is 0 because this vector is a vector which is orthogonal to u, and then when I multiply it by u, dot product, it becomes 0. So it gives me one equation, so it becomes m plus n times u dot v equals to 0. So let me keep it for the future. Another thing that I want to do here is to dot product both sides of this relation by the vector v this time. Okay, so this becomes v dot, and then I will have u cross v. On the right hand side I will have m u dot v, and this time v dot v becomes 1 and I will get n. Okay, what I want to use here is the cyclic property of the triple product. So if I have three vectors a, b and c, then this combination is called the triple product of these three vectors. And there is a property which is called the cyclic property of the triple product. I can write this equal to c dot a cross b, and I can also write it as b dot c cross a. Okay, so the proof of this is independent of the proof of the BAC-CAB theorem. So if you have studied this before, you will see that the absolute value of this number is equal to the volume of the parallelepiped constructed on these three vectors as the edges passing through one vertex. Okay, and here, for example, you put the parallelepiped on the ground, on the base, which is on the base, the parallelogram base, which is constructed on the vectors b and c. then it can be interpreted as putting the same parallelepiped, but this time put that face which is constructed on vectors a and b, and so forth. So it means that it is completely clear that the absolute value of these numbers should be the same, because all of them represent the volume of a single parallelepiped. Okay, and then you can convince yourself about the directions and things like that. So what I'm saying is that this relation is completely independent of the proof that we want to have here. So this comes a priori to the BAC-CAB rule, then I want to use this for proving that. So here I will give the role of A to this vector, give the role of B to this vector, and give the role of C to this vector, and then use the cyclic property. So what can I do? I can write it as U cross V as my C vector, dot V cross U as, so this, you see, this is C and this is BA and this is B. So CA cross B is equal to A dot B cross C. Okay, and then right hand side I will have the same thing. So MU dot V plus N. But you see that this vector and that vector are almost the same. I write minus, and then I will write this vector multiply dot product by itself exactly. So what I have done, I have interchanged these two and I put a negative sign here, and on the right hand side I will have mu dot v plus n. But of course this can be written as the norm of vector u cross v squared is equal to mu dot v plus n. But what can I do? I can write minus norm of u, norm of v, sine of the angle between them, so let me call that angle theta, to the power of 2 equals to mu dot v plus n. But the norm of this vector is 1, that's a unit vector, the same is here, so I will get minus sine squared theta equals to mu dot v plus n. But then let me continue here. So what you have, instead of sine squared, we can write 1 minus cosine squared theta equals to mu dot v plus n, and then it becomes cosine squared theta minus 1 equals to mu dot v plus n. Yes? But if I ask you what can I write instead of cosine, it is clear that I can write u dot v. So let me change my color. So if I ask you what is u dot v, you would say this is norm of u, norm of v, then cosine angle of them. But norm of u and norm of v are both equal to 1, so this becomes simply cosine theta. So then this means that this relation can be written in this form, that u dot v squared minus 1 is equal to mu dot v plus n. Yes? So I have this relation here as well. And then what I have to do, I have to take this equation and that equation into a system of equations and solve for the unknowns m and n. Okay? But this is better, so let me go back here. From here I can find that m is equal to minus n u dot v, and then I will replace it here in this equation. Yes, I will get u dot v squared minus 1 is equal to, instead of m I put that expression, so it becomes minus n u dot v squared plus n. And then if I move everything to the left hand side, this becomes n u dot v squared plus u dot v squared, and then I will have minus n minus 1 equals to 0. So here I can factor u dot v squared out, then I will have n plus 1, and then take a minus sign out from the last two terms, it becomes this, and finally I factor n plus 1 out, and I will get u dot v squared minus 1 equals to 0. So this will tell me that either the first one is 0 or the second one is 0. But the second one cannot be 0 because I am assuming that u and v in this case are non-parallel vectors. So the second bracket is not 0. So it means that there is only one possibility in this case, and that is n equals to minus 1. Okay, and when n is equal to minus 1, I will take it and put it here. I immediately find that m is negative u dot v. So this means that, let me write it just here, m is negative u dot v. So this is my m. Yes? And now, if I go back here, do you remember? This was the identity that I have. Now I realize that this is positive. This is positive. So I have to correct that, because n was negative, so this means that m is positive m is positive u dot v. Yes? Okay, now what happens if I go here, I take a now here in this equation, instead of m I put u dot v, and instead of n I put minus 1, and then immediately I get what I expected. Yes, so that I finish this one. So this is the proof for this very special case. This very special case tells me that, so let me now put it in a box because we want to use this one for the second part. So here it tells you that the BAC-CAB rule works if I have two unit vectors, so that I want to find this cross product, but so that these are unit vectors and one vector is repeated. If that is the case, then this tells me that I can safely use the BAC-CAB rule. Okay? Okay. Now, of course, we have to go to a little bit more general case. So for this case, what I will do, again, I will not attack the main problem here. I want to also talk about another special case. Here I will consider three vectors, but unit vectors. So I want to show that u cross v cross w, all of them unit vectors, but of course they might be completely different vectors. In the previous case, I considered two vectors, not three vectors, but here I'm considering three vectors, and I want to show that the same rule will apply, the same BAC-CAB rule. So I want to show that this is indeed the case. Oh, sorry. So this is what we want to show in this case. Also consider some special cases. First, let us consider the case. So I want to consider that if v is parallel to w, what happens? If v is parallel to u, what happens? If u is parallel to w, what happens? So I want to show that in all these special cases, this is automatically satisfied without having a very big problem to prove it. This is very simple. Yes, if v is parallel to w, then we know that v cross w is the zero vector. So this means that the left hand side becomes the zero vector. Okay, but what happens if v is parallel to u? It means that I have two possibilities for v and w because they are unit vectors. Either they are completely equal, or one of them is opposite the other one, yes? Okay, what happens for v? So for the right hand side, I can consider two cases. One case is what happens when v and w are the same. So then what can I do? for the right hand side, wherever I see W, I can replace it with V. So then it becomes V U dot, instead of W I put V, minus W I put V, and then U dot V. And apparently this is equal to the 0 vector. What happens if W is equal to minus V? So wherever I see W, I replace it with minus V. So this becomes V U dot minus V minus minus V multiplied by U dot V. But of course, the first one becomes minus V U dot V, and then positive V U dot V. And then again, this becomes the 0 vector. So for this case, you immediately realize the left-hand side is the 0 vector, and the right-hand side for both possible cases is the 0 vector. So this means that the left-hand side is indeed equal to the right-hand side for this special case. Yes? Let me consider one more, and the other one you can do it yourself. So let us consider this one. So again, when we say that V is parallel to U, then what happens? Then I have again two scenarios. Either V is exactly equal to U, or V is equal to negative U, because these are unit vectors again. But then what can I do for the left-hand side? Wherever I see, for example, let us consider this case. Wherever I see V, I replace it with U. So then it becomes U cross, and then instead of V, I put U cross W. Yes? But this becomes the previous special case in which these two vectors are the same. So I can apply the BAC-CAB rule for this special case as we showed earlier. So this becomes U dot W minus W. Yes, so that would be my left-hand side. But if I go and calculate the right-hand side for this, here I replace V with U everywhere. So it becomes U, and then I will have U dot W, and then I will have minus W, U dot U. But U dot U is 1, so that becomes U dot W minus W. And you see that again, the left-hand side is equal to the right-hand side. Yes? So for the other part, for this one, you can do exactly the same thing. And you can also do this one yourself. So it means that if any pair of these vectors involved are parallel, then we are done. So in what follows, we assume that none of these vectors, no pair of these vectors are parallel vectors. So we are assuming that V is not parallel to U, V is not parallel to W, U is not parallel to W. So in what follows, I am assuming this. Okay, how should we prove this? Again, the idea is the same. So what I have to do, I have to say that, okay, there exists, let me write S and T in R such that U cross V cross W is SV plus TW. And then by multiplying by U both sides, dot producting by U, then you will get immediately that if I multiply this by U, this becomes 0, and then this becomes S U dot V plus T U dot W equals to 0. Then I need to find another equation to solve for S and T. But the idea here is now I dot product everything here, for example, by V. So what happens? Then it becomes V dot U cross V cross W is S, V dot V is 1, and then plus T V dot W. Then I can use the the cyclic property of the triple product, but I want to do it 2 times. So what happens is becomes V cross W and dot V cross U. I use the cyclic property once more, so I will consider this one unit vector. When one vector, the second vector, the third vector, I use this property once more. So then it becomes U dot V cross W cross V. Yes? And then what I do, I write it as minus U dot, and I interchange V and V cross W. Yes, so what I have done, I replace these 2 vectors and I put a minus sign here, and then I can now write the right hand side here. So it becomes S plus T V dot W. Okay, why I did this? Because now here I can use the BAC-CAB rule for the case that I have unit vectors, one vector is repeated. So then it becomes minus U dot, if I use that rule, it becomes V dot W minus W is equal to S plus T V W. And then I multiply this vector in, so let me multiply this by that first. It becomes positive U dot W minus U dot V dot W is equal to S plus T V W. Okay, so that is also another relation. Okay, now what we say is this. If U dot W and V dot V, U dot V are both equal to 0, we are done. Why is that? Because if this is 0 and this is 0, then the right hand side becomes the 0 vector. But what is the meaning of this being 0, this being 0? This means that U is orthogonal to W. Yes. The other one means U is orthogonal to V. So it means that U is parallel to V cross W. Then in that case, the left-hand side becomes 0 as well, because these are parallel vectors. So it means that if this is 0 and this is 0 simultaneously, the right-hand side becomes a 0 vector, and because this vector turns out to be parallel to this vector, the left-hand side also becomes a 0 vector, and we are done. So in what follows, we can assume that at least one of them is not 0. Okay? Either this one should not be 0 or that one. For simplicity and definiteness of discussion, let me assume that U dot V is not 0. Okay? Why is that important? Because now if U dot V is not equal to 0, I can multiply both sides of this by U dot V. Then you will get U dot W minus U dot V dot W. Yes, and this becomes equal to S U dot V, and then plus S U plus T U dot V dot W. Okay, why this is good? Because now from this equation you realize that S U dot V is equal to minus T U dot W, and then I can take this and put, instead of S U dot V, I can put minus T U dot W, so this becomes equal to minus T U dot W, and then I will have T U dot V dot W. Okay, and I can factor a T out. This becomes U dot V dot W minus U dot W. Yes? And now look here, the left hand side is this, the right hand side is that one. So what I can do, I can move this to the left hand side, And then you see that this factor is exactly this factor, but this minus sign is here. So when I move it to the left hand side, this becomes positive, this becomes negative, and that becomes exactly this factor. So let me just write it here. So then it becomes u dot v, and then I will have u dot w minus u dot v, v dot w, and then you have plus t, and then I will write u dot w first minus u dot v and v dot u, v dot w, sorry, equals to 0. Yes? And then what I do, I factor this out, so it becomes u dot w minus u dot v, v dot w. And then from the first one, u dot v is left, from the second one, t is left, equals to 0. So then I have two possibilities. Either the first one is 0 or the second one is 0. Let us concentrate for the time being on the second one. So what will happen? The second one will give me, so let me see that. Let me write this. Either this one is 0 or this one is 0. If this one is 0, this will give me that t is equal to minus u dot v. Yes? And then, if I plug this back here, I will get that s u dot v is equal to minus u dot v times u dot w. But because I am assuming that u dot v is not 0, I can cancel it from both sides. And then I immediately get that s is equal to positive u dot w. Yes, so let me repeat it here for you again. So I have s u dot v. Instead of this t, I put minus u dot v, so then it becomes positive u dot v multiplied by u dot w. But I am assuming that here u dot v is not 0, so then s becomes exactly this, and that's exactly what I have written here. Now if you go back and take s away and put u dot w, you see you will get exactly this one. And if you take t away and put minus u dot v, you get exactly this one. So you see, I have two possibilities. If this happens, the BAC-CAB rule in this case is proved. I need to consider what will happen if I have this scenario. Okay, so let me take this one with me to the next page. So I move that equation here. So let me go back again. So here we realize that either this one is 0, which we are done, because what we get from here gives me exactly the BAC-CAB equation. Another possibility is this one to be 0. I want to show that even if this is 0, again the BAC-CAB rule applies. But that would be a little bit tricky. So how should I do that? I first interpret this a little bit differently. So from here, I can factor the vector minus u out. Then this vector becomes negative w, and I will write it here. But this becomes v multiplied by v dot w. Yes, this is equal to 0. So if you want to check it, you can multiply it back. This multiplied by that one will give me this. Okay, I have to write this as the hat, because these are unit vectors. And then if you multiply this here, you will get exactly this term. So what I have done is completely right. But then I can use the BAC-CAB rule for the two vectors v and w only, unit vectors. So what can I write? I can conclude that minus u, all of them are hat actually, u hat, and then instead of that vector I would write it as V cross W, because I know that the BAC-CAB rule holds for this. We can check that this BAC-CAB, it gives me exactly this, because V is the unit vector. Okay, but now I can use the cyclic property. Of course I can drop this minus sign here, because if this combination is 0, I can divide by a negative sign, and then I can get rid of this negative sign here as well. And then what I can do, I can use the cyclic property of this triple product. I can bring V cross W out, dot U cross V equals to 0. So what does this mean? This means that this vector and this vector are perpendicular. Okay, what is this vector? This vector is a vector which is perpendicular to V and W simultaneously. And we are considering the case that V and W are not parallel, so this means that this vector is perpendicular to the plane that contains these two vectors. Yes? For example, if I want to draw something here, so I can consider this case. So let me just draw it in this way. So assume that this is one of my planes. Yes, I have another plane perpendicular to this. I will tell you how we have to imagine this situation. So assume that something like this we have. Okay, and then this vector, so this is the way that I am thinking about. So this vector, assume that this vector is the unit vector V, and this vector in this plane is the unit vector U, and this vector in this plane is the unit vector W. So that is exactly the meaning of this equation. So here V cross W is a vector which is perpendicular to the plane containing these two vectors. And as you see, it is right, because if I cross product them, it becomes perpendicular to this plane that you see here. And then U cross V is a vector which is perpendicular to both U and V. So then it becomes perpendicular to the plane containing these two. So this equation can be geometrically interpreted in this way. The plane containing these two vectors, this plane, is perpendicular to the plane containing these two vectors, this plane. Yes, that is the meaning of that. But then hopefully you can immediately realize that you can conclude that V cross U is parallel to V cross W. Yes, because what is V cross W? V cross W is a vector in this direction. And then what is V cross U? V cross U will be a vector which goes to the back of this one, and it's perpendicular to this plane. And then you multiply it by V again. So V multiplied by that becomes, it goes actually down, but it becomes perpendicular to this plane. But anyway, these two vectors are parallel, because V cross W in this picture that I have drawn for you, for example, is pointing upwards, and this vector would be something pointing downwards. So these two vectors are parallel. But if I ask you, what can I write for this? I can use the BAC-CAB rule for this case that two vectors are the same. So I can say that V times U dot V minus U, instead of this expression, I can write this, is parallel to V cross W. But I know that V and W are non-parallel, so this is a non-zero vector. And this is also a non-zero vector, because if this is going to be a zero vector, then vector U is a multiple of vector B, and this means that U and B are parallel, but we have already considered the parallelness of these two vectors, And now I'm solving the problem for the case that none of these vectors are parallel. So this means that there is only one thing going on, and that is the cross product of this vector and that vector should be equal to 0. Yes? So then what I do, I take this vector and cross product it with that vector. But we know that the answer should be the 0 vector. But then I use distributivity. I distribute this here and there. So what I get is this. It becomes V. So let me write that one first. It becomes U dot V and then V cross W minus U cross V cross W is equal to the 0 vector. Then I move this one to the other side and I use the BAC-CAB rule for this case. So it becomes U dot V and that becomes V dot W minus W. And on the right hand side I will have U cross V cross W. Yes? And now one more step. I multiply this number in, so this becomes V U dot V dot W minus W, and then I will have U dot V equals to U cross V cross W. Yes? But now let us go back here, you see. Let me make it a little bit smaller. So here I have this condition. So it means that instead of U dot V times V dot W, which is this expression, I can simply write U dot W. So then it becomes V U dot W minus W U dot V is equal to U cross V cross W. So it means that again I was able to get the BAC-CAB rule for this case back. Yes, that is exactly what we wanted to prove. So BAC is VU, that's exactly this term, and CAB. So that's everything is correct. So it shows that in both cases I can show that the BAC-CAB rule for this case is true. And now finally I want to go back and prove this for any arbitrary vectors A, B, and C, not just unit vectors. Okay, so let us take this with us to the next page. We want to prove this. So let me have it in front of our eyes. So we want to prove this one now. I would say now the proof is simple. I would say that if at least one of these three vectors is it the 0 vector, we are done. For example, if A is the 0 vector, the left hand side becomes the 0 vector. A is the 0 vector, this vanishes. A is the 0 vector, this vanishes. I am done. If B is the 0 vector, again this whole thing becomes the 0 vector, but because B is 0 vector, this is cancelled and this is also cancelled. So you see that if one of these vectors is equal to 0, then I am done. So I will prove it for the case that none of the vectors are equal to 0. Okay? So if A, B, and C are non-zero vectors, I define this unit vector EA to be 1 over norm of A multiplied by this vector. So that is the unit vector on the vector A. I am dividing this non-zero vector by its norm, so it becomes a unit vector on the vector A pointing into the same direction. And similarly, I define these for non-zero vector B, and I also define this for the non-zero vector C. Okay. But now one thing I know, for the unit vectors, I know the BAC-CAB rule applies. So this means that EA cross EB cross EC is equal to EB times EA dot EC minus EC EA dot EB. Yes. And now what I do for EA, I can write this, and for EB this, and for EC this. So what will happen? It becomes 1 over norm of A cross 1 over norm of B cross 1 over norm of C is equal to 1 over norm of B, and then 1 over norm of A dot 1 over norm of norm of C, and then minus 1 over norm of C, 1 over norm of A dot 1 over norm of B. Yes, and then hopefully you realize what's happening, because these are constants, so I can write them as 1 over norm of A, norm of B, norm of C, A cross B cross C. On the right hand side I can take these two out, so it becomes 1 over norm of A, norm of B, norm of C, B, A, C, and the same thing for the second term, so norm of A, norm of B, norm of C, and then I will have C, A dot B. Yes, and then it is clear that I can take this common factor out, then I will get my BAC-CAB equation finally. And that is exactly what we were looking for. So if I want to review what we have done, so if I go to the first page, my goal was to prove this for arbitrary vectors A, B, and C in all possible cases. First, I proved a similar argument for the case in which I am facing unit vectors and one unit vector is repeated. Okay? And I was able to show this, and then next I will showed it for the case that I have 3 vectors, but all of them are unit vectors. That was a little bit lengthy, and after that, using the idea of the proof, using that fact for unit vectors, I was able to finally prove this formula. So the only thing that I have used here was mainly was the cyclic property of the triple product. Promise in the beginning of the video, I want to prove the BAC-CAB identity using the tensor notation. I will not explain the details. I'm just presenting this for review for the people who already know these topic. So here I just remind you that if I have 2 vectors A and B, A with components A1, A2, and A3, B with components B1, B2, and B3, we have A dot B using summation convention. This is AI, BI. Repeated index means it is summed over from 1 to 3. And then if I want to find the ith component, I can be 1, 2, 3. Of this cross product, this becomes the epsilon ijk, Levi-Civita symbol, the jth component of the first vector multiplied by the kth component of the second vector. So here I want to show that the vector on the left is equal to the vector on the right, so I will take every component of this, for example the ith component, I is 1, 2, 3, and I show that each component of the vector on the left is equal to the ith component of this vector on the right. Okay, so what I do, I will start from A cross B cross C, the ith component. According to this rule, I give the rule of this little a to this A and this B cross C to this. what happens? This becomes epsilon I j k, the first vector, jth component, so it becomes a sub j, and then the second vector, which is b cross c, kth component. But then epsilon I j k, I just repeat these things, and then I use this formula again for this part. So I should have a Levi-Civita symbol which starts with k, and then I have two other indices, for example L and M, and then I have B, L, C, M. Okay, but then what I can do, instead of epsilon ijk, I can write epsilon kij. They are exactly the same thing. And then I put epsilon klm next to it, and then I will have aj, bl, and cm. But there is a formula for the product of these two epsilons. This becomes delta il delta jm minus delta im delta lj. Delta is the Kronecker delta. It is equal to 1 if these indices are equal, and that is equal to 0 if the indices differ. So then multiplied by aj, bl, cm. And then I multiply this in, so it becomes delta il delta jm minus delta im, times aj, bl, cm minus delta im delta lj aj bl cm. But now this delta actually kills the summation over L and turns L to an I. So this becomes bi here. I can keep aj, and then this delta kills the summation over M and turns M to a J. So this becomes Cj. And then I will have minus. Here the same thing. This delta will kill the sum over M and turns M to an I. So the last one is Ci. And this delta will kill the summation over L and turns L to a J. So this becomes Bj. This is I, Bj, and then I have Aj. And then I can write them here in this form. I can write Aj, Cj, Bi minus Aj, Bj, Ci. Then Aj, Cj is nothing except the dot product of A and C multiplied by Bi, and then Aj, Bj is the dot product of A and B multiplied by Ci. Now if you go back, the ith component of this vector is equal to this, which is exactly the ith component of this vector. And this can be done for any I, 1, 2, or 3. So it means that we were able to show that each component on the left is equal to the corresponding component on the right. Okay, I hope that this video was useful for you. Until the next video, be safe and take care. Thank you.